Okay, perfect. So we're going to be doing a little bit of physics today, and we're going to start off from where we left off last time. So I've just got a few questions, okay, to begin. Can anyone state the unit of force? The unit. So if my whiteboard works correctly. Yes, what is the unit of force? Feel free to just write it down somewhere or just say it out loud. Okay, so yep. So Alyssa, I saw you started writing newtons, and yeah, that is the correct answer. The unit of force is newtons, and the symbol to represent that is the capital letter N. Okay, so joules is the unit of energy. Okay, so joules measure how much energy there is in a system or how much energy is being transferred, but newtons measures the amount of force being exerted on an object. When you push something, pull something, you're exerting a force, and newtons measure that. Okay, but when you push something, you're also transferring energy, and the amount of energy is measured in joules. Now, energy and forces are different things. So to kind of think about it, you can think of, so if you think about water, and if you think about water at different temperatures, right? Water at 60 degrees Celsius, assuming that the water is all the same mass, water at 60 degrees Celsius is going to have more energy than water at 30 degrees Celsius. But, and that's what energy is, but with forces, there is going to be 0 newtons of force on that water unless you push it or pull it or something like that. You push this container of water. So forces are all about the motions being exerted on an object, whereas joules is how much energy that force is carrying. Okay, what is the name of the apparatus? So the apparatus, the tool that is used to measure force. Yeah, very good. A Newton meter. And yeah, a Newton meter, it kind of looks like a set of scales, but it's to measure force, not weight. Not like bathroom scales where you measure your weight. Okay. Can you give me, let's say, an example of a contact force? Yeah, friction. That's good. Can you give me maybe like another one as well? Yeah, resistance. Okay, very, very good. And then the final question, can you give me an example of a non-contact force? Yeah. So the force of magnetic pull. If you were to use the actual word to describe the force of magnetic pull is called magnetism. Magnetism. Okay, and that is the force which describes like magnets. And earlier I saw gravity as well. Yeah, that's correct as well. Um, Now, in reality, the name of the force, remember, caused by gravity is called weight. So weight is actually the name of the force, which is caused by gravity. But saying gravity is correct as well. There is another non-contact force, like another very, very like common non-contact force. So we have magnetism, we have weight by gravity, and then we also have electro. Can you finish it off? Yes. Yeah. So we have electrostatic force, which is forces applied onto charged objects. Like charges, when I say like charges, I mean charges which are the same. So positive and positive, or negative and negative, they repel. And opposite charges, so positive and negative, attract. Okay. Okay, so last time, if you remember, we were looking at some force diagrams as well. So diagrams which describe forces and how they act on an object. So let's say we had an object here, okay? And let's say it was being pulled with a force of 12 newtons. But it was being pushed as well from behind. And let's say it was being pushed by a force of 16 newtons. Okay? What is the resultant force and what direction is it acting in? Yeah, 28 newtons. And forwards. So the resultant force is going to be 28 newtons to the right. And then likewise, if I just quickly do another example, if I have another one of these objects and it's being pulled again, 12 newtons to the right, but this time it's being pulled to the left by 16 newtons. What is the resultant force? Yep, 4 newtons to the left. 16 minus 12 gives you 4 to the left. Okay. Now, just bear with me a second. Okay. And what if then we have another object with a force of 6 newtons acting upwards and also 6 newtons acting downwards? What is the resultant force? Yep, there is no resultant force. Now, the important question now is, what happens if there's no resultant force? What is this object going to do? There's two things that, okay, so it won't move, okay? So you've said it won't move, but under what conditions will it not move? Because what if it was already moving? Will it stop moving if it was already moving? Yeah, so if it was already moving, it will continue moving at that same speed in the same direction. So, yeah, if it is moving, it will continue to move at the same speed. However, if it is stationary, then yes, it's going to just stay stationary. It's going to just not move. Let me just shrink out this whiteboard a little bit for the recording. Just bear with me a second. Okay. Yeah, and if it's stationary, then it's going to remain stationary. But it's very important to remember that if an object has no resultant force, it doesn't necessarily mean it will not move, okay? Because if it was already moving, it will just continue moving at the same speed. And if you think about a car driving on a motorway, let's say you're driving at 70, the reason why you have to keep the gas pedal pressed down is because if you think about the car, acting backwards, you have the force of friction and air resistance, okay? So there's a resultant force acting backwards. And if there's a resultant force acting backwards, then the car is going to slow down until it stops, unless you press the gas pedal to balance it out so that there is a driving force forwards, which is equal to the resistance forces backwards, so that in total there's no resultant force. And then you can keep the car going at 70 miles an hour. Okay? Right. Now, we also touched a little bit on Newton's laws of motions last time, okay? And we had a big focus on his first and third law. Does anyone remember Newton's first law? If I, okay, yeah. I'll write it out here, actually. Newton's first law. His first law is the pretty simple one. It's the one, well, the little question we did right now with the resultant forces and is the one with no resultant force. That kind of ties in to Newton's first law, if you kind of remember. Yeah, yeah, okay, so an object remains still if it has equal forces, okay. So what you mean by that is when you say equal forces acting on it is if you have, a force on the left and you have an equal force on the right. But you can just say no resultant force, okay? So you can say if an object has no resultant force, then it's going to remain stationary or travel at constant speed. So yeah, that's Newton's first law. So an object will be stationary, so just not moving, or travel at constant speed unless acted upon by a resultant force. So unless there's a resultant force, an object is going to just remain stationary or travel at constant speed. And as long as you word it somewhat like that, so yeah, that would be completely fine in any exam. Okay, so that's Newton's first law. Last time we didn't really focus too much on his second law, so we're going to talk about Newton's third law now, okay? Does anyone remember Newton's third law? Yeah, has some opposites. When you say opposite, can you like elaborate a little bit more, maybe? Okay, no problem. So every force acted on an object. Okay, so for every force which acts on an object, okay, there is an equal and opposite force. So if we think, if I just draw an example, if we have a cube, and that cube is just sat on the floor, if the cube is exerting a force of 2 newtons downwards because of weight due to gravity, then the ground is going to be exerting a force of 2 newtons, so an equal but opposite, because it's the same size, the force, but it's opposite in direction, okay? So Newton's third law is just simply for every force which acts on an object, okay, there is going to be an equal force in size but opposite in direction acting on the other object. Okay, so that is Newton's third law. So if we're thinking back to some of the previous examples, remember, if there is a resultant force, that object is going to move. So if you have something sat on the floor and it's exerting a force of 2 newtons downwards, if you don't have Newton's third law happening and you don't have that 2 newtons upwards, then the object is going to move through the floor, basically. So there is Newton's third law. When two objects interact, for every force exerted, there is an equal and opposite force exerted on the other object. Okay, so that's Newton's first and third laws. Okay, but let's look a little bit now at Newton's second law. Okay, so Newton's second law, I would say, is probably the easiest one to remember, because so far all we've been doing is we've been talking about forces, but we haven't really linked forces to anything else, because let's say you pushed a block, a wooden block, and let's say this wooden block weighs 1 kilogram, okay? Let's say you push this wooden block with a force of 10 newtons. And then let's say you pushed another block with 10 newtons again. But this block is made from a very, very dense metal, so it's very heavy. Is the same thing going to happen? No, right? The heavier block is going to be harder to push. So how can that be explained? Well, that's explained and described by Newton's second law, which is basically a simple equation. F is equals to m times a, where F is the force being applied to an object, okay, m being the mass of an object, and a being the acceleration. Okay? So can anyone explain to me what they think acceleration means? Moving forward at a speed, okay? Okay, but then what does speed mean then? Because wouldn't speed mean moving forwards at a speed? How fast an object moves, okay? When it's idle. Okay, I honestly, I know what you mean. I see where your thinking is at. Because you're thinking, okay, you have an object and it's stationary, it's idle, like you said, okay? And you're thinking about how fast it changes. So it's initially not moving, and you're trying to explain, okay, how fast can it go from not moving to moving? Okay, yeah. That's very good thinking, okay? We're going to cover a bit more about acceleration now, okay? So let's think about distance, speed, and acceleration, okay? So if we just go down here to underneath the Newton's laws on the whiteboard. So distance, that is the easiest one to understand. So distance is simply how far an object has traveled, okay? So if you throw a ball and you throw a ball a distance of 20 meters, it just means that ball has traveled 20 meters, okay? Speed, on the other hand, is simply how fast an object moves. But another way of saying that is the rate at which distance is covered. Okay, so if you have a ball and you throw it 20 meters, that is the distance the ball travels. The speed of the ball tells you how quickly that distance is covered. Okay, so if you have, if you're throwing this ball 20 meters and it takes 20 seconds for that ball to travel the 20 meters, then you're traveling 1 meter of distance every second. That is your speed. And we actually have an equation to describe distance and speed. Okay? So speed is equals to distance over time. Now, have we seen this equation before? Yeah, okay. So speed is equal to distance over time, but you can rearrange that equation as well. So can can you guys rearrange this for what distance is equals to? So if I were to write this as s is equals to d over t, yeah, distance is equals to the speed times time that it takes. Because if you think about it, if an object has a speed of 5 meters per second, okay, and it travels for 10 seconds, well, if it's every second is traveling 5 meters, in 10 seconds, it would have traveled 50 meters, right? So it's quite intuitive, okay? Now we're going to talk about acceleration. Acceleration. And acceleration, if you think about speed and what speed is to distance, that is essentially what acceleration is, but to speed, okay? So acceleration is how fast an object speed changes, okay? That's all it is, how fast an object's speed changes. Or you could say the rate of change of, of speed, okay? Because let's say you have an object which is not moving at all. It's stationary, so 0 meters per second, but it eventually begins to move at 10 meters per second, okay? So acceleration is the measure of how quickly it changes from 0 meters per second to 10 meters per second, okay? Because if it goes from 0 to 10 in 10 seconds, that means that every second the speed is increasing by 1 meters per second. So you would say the acceleration would be 1 meters per second, right? Per second. And that looks a little bit weird, okay, that unit, because it's meters per second. But if you think about it, it does kind of make sense, because the speed is changing by 1 meters per second for every second, okay? Now, another way to write that is to just say 1 meters per second, right? Which just simplifies to 1 meters per second squared, okay? Because essentially what you're saying is meters per second times by per second. So that gives you the unit of acceleration. Okay, so let's say we have an object traveling at 5 meters per second, and then it accelerates to 15 meters per second in 20 seconds. Okay? Can you tell me what the acceleration of this object is? Now, if you think about the equation for acceleration, remember? So acceleration is equals to the change in speed. So in maths, when we say change, we use this symbol, delta. Change in speed divided by the change in time. So the change in the speed of an object divided by the time taken for that change of speed. That is the definition of acceleration, right? So yeah, so change in speed is 10, change in time is 20, and that would give you an answer of 0.5. And what about a unit? Remember to always put your units, because in an exam, even if you just put 0.5, you're not going to get all the marks without your units. Yeah, you might struggle to write that on a keyboard, but yeah, meters per second squared, remember, okay? Very important, meters per second squared. Okay, so we know what distance, speed, and acceleration are now. How can we link that back to force? Well, Newton's second law, okay? Newton's second law, which is F is equals to m times a, basically says the force that an object is feeling is equals to the mass of that object times the acceleration of that object. Okay? So in the question we just did right now, the 5 meters per second to 15 meters per second in 20 seconds, we calculated that the acceleration is 0.5 meters per second squared. Okay? But let's say we give a mass to this object. Let's say this object has a mass of 2 kilograms. Okay? So mass is equals to 2 kilograms. Can you tell me what force you would have needed to have exerted to move this object of 2 kilograms from 5 meters per second to 15 meters per second in 20 seconds? What force would you have needed for this? Okay, so 20 newtons you said. Okay, so Newton's second law, the equation F is equals to m times a, okay? So we know m, the mass, is 2. And the acceleration is 0.5. Okay? So 2 times 0.5 just gives you 1 newtons. Do you kind of see how I got the answer? So we're just using the equation F is equals to ma. And we're subbing in the values of m and a. Okay? Now, can you rearrange this equation to find what acceleration is? Okay? So F is equals to ma, but what would a be equals to? What would acceleration be equal to? Well, if you think about this equation, there's 2 ways to think about it. You could think about it firstly as an equation triangle. I'm not sure if you guys have seen these yet, but you can draw like a triangle or a pyramid, however you want to call it. And you can put your values in. So, and if you cover up 1, if you cover up the one that you want to find, it'll tell you how to find it. So if you cover f, well, to find f, it's m times a. If you want to find what a is, cover a is equals to f over m. Yep, f divided by m. But if you want to approach it more mathematically, we have f is equals to m times a. Okay, if we divide both sides by m, the m's cancel out on the right hand side, leaving you with f over m on the left hand side is equals to a. Okay, so that's a more mathematical way to think about rearranging equations. But yeah, acceleration is equals to the force exerted on an object divided by the object's mass. So let's say we have an object of 10 kilograms. And there is a force of 16 newtons acting to the right, okay, but a force of 4 newtons acting to the left, okay. If I were to ask you, what is this object's speed in 10 seconds? Okay, so how fast will this object be moving in 10 seconds? So what would the first step be to try to calculate that? We know that speed is going to be related to acceleration. And we know that acceleration is linked to force. So what would be the very first step in figuring something out like this? Yep, so we find the resultant force. So the resultant force, which I'm going to label as RF, resultant force, is 12 newtons to the right. Okay, so we now know its resultant force. And remember, Newton's first law, right? If it is a resultant force, the object is going to begin moving. It's going to start to accelerate. Okay, so what's going to be the next step? Because we want to find what this object's speed is going to be in 10 seconds. Because the speed of that object is going to be changing over the next 10 seconds. So what piece of information are we going to want to find out? Yeah, so we're going to want to find out the acceleration of an object. And going back to the equation, F equals ma, or the rearranged form, A equals F over m. The force is 12 newtons. The mass is 10 kilograms. So 12 newtons over 10 kilograms gives us an acceleration of 1.2. Yep, very good. 1.2 meters per second squared. Okay? So that is the acceleration, okay? And remember, what that is essentially saying is the speed is increasing by 1.2 meters per second every second, okay? That is all what it means. So how fast will this object be traveling in 10 seconds? What will its speed be in 10 seconds? Yeah, 12 meters per second. Yeah, very good. Because if it's increasing by 1.2 meters every second, then in 10 seconds, it will have a speed of 12 meters per second. Okay, so just knowing the force being applied on an object and the mass of an object, we can then calculate its acceleration and speed at any given moment in time. Okay, that's very, very good. So yeah, we can see how it's all starting to like link together. It's how it's starting to how we can start to use all of this information. Okay, so something else we're going to kind of talk about. We're going to go back to speed a little bit. Okay, so imagine you're in a car. Okay, you're in a car and initially you're driving on a motorway. So you drive a little bit at 70 miles per hour, but then you reach a town and you have to drive a little bit slower. You have to drive at 30 miles per hour. But then maybe you speed up a little bit because you go onto a faster road where you're now driving at 60 miles an hour. Okay? So we can see the speed is not constant. The speed is ever changing. But let's say overall, it takes, let's say it takes 3 hours to do the entire journey. Okay? And let's say the entire journey has a distance of 150 miles. Okay? Well, if we were just to use these two bits of information, okay, we have the time and we have the distance. Well, we can go back to that equation. Speed is equals to distance over time. Okay? Speed is equals to distance over time. The distance is 150 miles. Time taken is 3 hours. Well, that gives us a speed of 50 miles per hour. Yeah. But if we look at what we drew, right, with the car, it was initially going at 70, then at 30, then back to 60. Okay, so is this 50 miles an hour speed very accurate? What does this 50 mile per hour speed, what does it actually mean? The overall, the average. Yes, that is the average speed, okay? That is the average speed that this car travels over the length of its journey. Okay, let me just move this whiteboard down. Okay, now we can think about it by drawing a graph, a speed distance graph. Sorry, a distance time graph. So if I draw a graph here, if I can get my line straight, okay. So let's label the y-axis distance, okay? And we don't need to actually like put any values on. We just know that as you go up the y-axis, the distance is increasing, okay? Because we have 0 at the origin. And let the x-axis be time, okay? So if, change the color of the pen. So initially the car is traveling at 70 miles an hour, okay? What does that kind of look like? So remember, 70 miles per hour, that is the speed of the object, the speed of the car. And speed is simply distance divided by time, or the rate at which distance changes. Okay? So if it's going at 70 miles an hour, we could, let's say it looks something like that. Okay? So the distance is increasing as time is increasing. Okay? That kind of makes sense, right? But then the car slows down, so it's only going at 30 miles per hour. So that's what it's going to kind of look like. Okay? So yes, the distance is still increasing as time increases because the car is still moving. However, the gradient of the graph is not as steep. It's not as steep because the rate at which distance is increasing is not as big. Okay? But then the car is going to start traveling a little bit faster at 60 miles an hour. So it might look something like that. And again, it's not as steep as the 70 miles per hour one, but it's more steep than the 30 mile per hour leg of the journey. So here is traveling 70 miles per hour, then 30, and then back to 60. Okay, so that's how you can represent the journey on a distance time graph, where the gradients. So do you guys know what gradient means? Yeah, yeah, how steep the graph is. So yeah, the gradient of a distance time graph represents the speed. Because if you think about it, the gradient, like you said, represents how steep a graph is, and how steep a graph is basically the y-axis divided by the x-axis, okay? So the gradient is the change in your y-axis. Just bear with me. I don't know why, but the whiteboard has refreshed. Okay, I think we're okay. I don't know why that just happened. Anyways, the gradient is your change in y-axis over your change in x-axis, right? Because it's just measuring how much the y-axis increases over x-axis increase. And we know the y-axis is distance and the x-axis is time. And we know that distance over time is your speed. So that's how we know the gradient of a distance time graph is your speed. Okay, let's look at something a little bit more. If I were to draw another graph right underneath, okay? And again, let's label the x-axis as time. But this time, the y-axis, instead of being distance, let's say the y-axis represents the speed, okay? What do you guys think this will look? So again, we're going to be using the data from the car journey, the 70 mile to 30 miles per hour to 60 miles per hour one. You guys should be able to use the pen tool as well to draw. Would any of you like to have a go at drawing this graph? I can start the graph off, okay? So speed. Well, initially it's okay, yes, very good, very good. That's good. Yeah, so it's initially traveling at 70 miles an hour. Let's say 70 is right here. Okay, good. But then the speed is going to change. Okay, yeah. So let's say it's 30 miles an hour. And then it goes to 60. Yeah. Okay, so yeah, we'll say if I can draw this dotted line. We'll say it's 60 right here. Okay, cool. So one thing which the biggest thing I noticed was that you drew these lines here, connecting it all, right? And honestly, I say that is very good because that is actually what's happening in real life. Because in real life, you don't just instantly go from 70 to 30 just like that. You know there is some deceleration that is occurring, right? It doesn't just instantly go from 70 to 30. Now, in the question, I didn't actually talk about any like acceleration or deceleration. In the question, with the cars example, I genuinely just with just the data alone, it would kind of seem like the car is going from 70 instantly to 30 and then back to 60 again, right? But yeah, in reality, that is what's going to be happening. It's going to decelerate from 70 to 30 and accelerate to 60 again. But yeah, that is what the speed time graph is going to look like. Now, what is the gradient of this speed time graph? Remember, the gradient is the change in y value divided by the change in x value. Okay, guys, we only have 10 seconds left of the meeting. Okay, so if you guys, I'm going to post the link on the Google Classroom and press the new link and rejoin, okay? Hello. We'll just wait a few moments for Harry to join as well. In the meantime, so you were asking about the recording of the last lesson. Um, I've been trying to find like where the recording is, but like with the Vuv like recording, it's kind of weird how it works. I'm not actually sure where the recording file is stored. I'll still try to find it, but I'll post the whiteboard slide of the last lesson at least. But yeah, okay. Anyways, we'll just quickly just finish off this bit of the lesson. But yeah, from now on, I'm recording like on my own as well, just straight to my laptop, so I can have all the recording files myself as well. Anyway, so yeah, so what is the gradient of a speed time graph? What does that represent? If the gradient is the change in y value divided by the change in x value, okay? So the y value is speed. That's what the y-axis represents, right? And the x-axis represents time. So the change in speeds over time, what does that represent? If we look back to some of the equations from earlier, where did we put it? Okay, if we look back up to this equation here, if you guys can see that I've highlighted in the red box. Yeah, 40 is the changes in speed from 70 to 30. Yeah, but I just simply mean, what is the name? Like, what is the... You don't actually have to calculate anything right now. Just simply, what is the name of the gradient? What does the gradient actually represent? Well, you said the speed, right? You've got to remember, speed is just represented by the y-axis, right? Because over here, the speed is 70. Over here, the speed is 30. Over here, the speed is 60. So the y-axis tells us about what speed is. Okay. Remember, okay, the gradient is speed divided by time. And if you remember from earlier, that is a definition of acceleration. Okay? So the gradient, let me zoom in, the gradient of a speed time graph represents acceleration. Okay? So that is what the gradient represents. Because if you think about it, right? The car goes from 30 to 60, okay? So it goes from 30 to 60, and you can see that how steep the graph is will tell you how quick it accelerates from 30 to 60, because if it does something like that, well, it's going from 30 to 60 in a very short amount of time, maybe 5 seconds, okay? But if it's doing something like that, well, it's still going from 30 to 60, but it might be taking something more like 15 seconds. Okay, so the gradient is representing how fast the speed is changing. Okay, and we know that how fast speed is changing is what the definition of acceleration is. So yeah, you were trying to do a little bit of calculation earlier. And yeah, we'll do that. Let's say the car stops traveling at 70 miles an hour at 20 seconds, okay? And it reaches 30 miles an hour at 30 seconds, okay? So what will the acceleration be? Yeah, so 40 divided by 10, because that's the amount of time it's taking for that to happen, 4 meters per second squared. Yeah, okay, that is 99% correct. There's only one bit of information that we're missing, okay? Because if you just tell someone, okay, yes, this car is traveling at 70 miles per hour. Oh, sorry. Maybe I shouldn't have used miles per hour as a unit, because so far we've been talking about acceleration as in meters per second squared, right? Because that's the default units for acceleration. And technically, we can write miles per hour as like an acceleration as well. We could write it as miles per hour squared, but that's a little bit confusing. So we'll pretend that this entire time we were talking about meters per second, okay, instead of miles per hour. So 70 meters per second, 60, and 30 meters per second, okay? But anyways, if we just told someone that this car was initially traveling at 70 meters per second, and there's an acceleration of 4 meters per second squared over over 10 seconds of time, well, what is that person going to think? That person is going to think that this car is going to accelerate to 110 meters per second, right? Because if you just tell them the car is accelerating by 4 meters per second squared, they're going to think the speed is going to increase to 110. So what bit of information were we missing which we can put into our answer so that whoever is reading the answer knows exactly what we mean? It's just simply going to be a minus sign, okay? So instead of saying the answer is 4 meters per second squared, we say the answer is minus 4 meters per second squared. Because as you can see on the graph, the speed is decreasing, okay? So the acceleration is negative. You could say, another word to say is deceleration, but it's just, yeah, so it's just simply negative acceleration. So if it's the acceleration is minus 4 meters per second squared, and the object is initially traveling at 70 meters per second, well, over 10 seconds, the object's speed is going to decrease all the way to 30 meters per second. And yeah, that is exactly what we mean on the graph, right? So yeah, so today we've had a pretty good look at Newton's second law and acceleration and force and what that actually all means. Okay, so just before we end the session, without looking, can you write down the equation in Newton's second law? Yep, F is equals to m times a. Now, Alyssa, I saw you write initially F is equals to a. And you're probably thinking of, okay, F equals A and M, but you're thinking, okay, that doesn't look right. But it's completely fine. You can like F is equals to M times A and F is equals to A times M. They all mean the same thing. Like for example, like 2 times 4 is equals to 4 times 2. It doesn't make a difference. So both equally correct. Um, and in fact, I'll tell you now that during my GCSEs, I used to remember it as F is equals to AM. That is how I used to remember it because like it spells out fam, right? And when you're doing your GCSEs, it's all about thinking of these little things to help you remember. So yeah, honestly, just remember it however you want. MA, AM, it's all the same. Okay. So yeah, that was today's lesson. Do you have any questions for me about anything that I've covered today or anything that's come up in school? Yep, no problem. Okay. Um, Again, if you have any questions whatsoever, feel free to ask me on the classroom. So this whiteboard slide, I will post that onto the classroom alongside a recording for Owen as well. And yeah, I hope you enjoyed the lesson today. And okay, even though Owen wasn't here, I will post a short piece of work this week. Okay, Um, and then next week it's going to be back to biology. Okay, yeah, thank you very much for joining, guys, and I'll see you all next week. Okay, bye bye.